Hi everyone. In this video, we're going to be talking about area and volume for Math 1452 at Texas Tech University. So at this point, I'm going to assume that you've already learned how to find the area between curves and you've already learned how to find volume, but you are struggling to set up the questions and struggling maybe with the difference between vertically and horizontally simple. So we're going to break down step by step how to find the volume and area and how to set these questions up. So we're going to follow a step-by-step process. And the first step, whenever we're told to find the area between two curves, is going to be to sketch the region. So I like to treat these questions really as word problems. And the first thing that we're going to do is we're going to write down all of our known information and draw a picture. And that means we're going to identify what the question tells us to do and then draw a picture of the curves that it's asking. So we're going to sketch the region, and oftentimes we're also going to identify intersection points. And after we draw our scenario, we're going to determine horizontally or vertically simple. So we're going to determine if our region is vertically or horizontally simple. So if you are struggling with what horizontally and vertically simple mean, at the same place you found this worksheet, you should be able to find an activity on Desmos that explains the difference between horizontally and vertically simple. But our first step is to draw the picture and then determine that. So once we've determined if our region is horizontally or vertically simple, we need to write our integrand and we need to write our bounds. So first off, our integrand is going to identify the top and bottom functions if we are vertically simple. So if we're vertically simple, we're looking at top and bottom, right? So it all kind of makes sense. Vertical means to find top and bottom. And then we're going to find our left and right functions if we are horizontally simple. So again, horizontal means we're looking at left and right. Okay, so we find top and bottom, or we find left and right. And that's how we're going to write our integrand. And then we need to write our bounds using those intersection points that we found. So again, we're going to, if we're vertically simple, use the x values of the intersection points. And that's if we are vertically simple. And we're going to use the y values of the intersection points if we are horizontally simple. So one thing that I think it would be good for us to internalize is that x's are always vertically simple and y's are always horizontally simple, right? Whenever we're setting up our integrals, they're only ever going to use x or y. And if we want to use x, that means we're looking vertically. And if we're looking with y, we're going to be doing things horizontally. And so once we set this up, we are going to evaluate our integral. So evaluate and solve. So most of the work here is going to be done in the setting up. So these are the steps, and I'm going to go ahead and scroll down here, specifically looking at this first part here that I'm going to highlight. Okay, so these are going to be the two different setups. So if we're vertically simple, we're going to have our integrand be our top minus our bottom, and we're going to integrate from left to right. So whenever we're plugging in our bounds using the first fundamental theorem of calculus, we always do top minus bottom or right minus left. So one thing to also internalize is that it's always going to be top minus bottom and right minus left. Because if we look over on the horizontally simple side, well, now our integrand is right minus left, and whenever we evaluate our bounds, it's top minus bottom. So really determining horizontally and vertically simple is using the graph to determine, well, which ones do I subtract first? Do I subtract top minus bottom in my integrand and then right minus left in my bounds, or is it vice versa for horizontally simple? So this is the setup for area. And so the setup for area is going to inform a lot of our setup for volume. So the next question is, how do I find the volume of a region using cross sections? And it's going to be the exact same steps as finding area, but the integrand is going to be an area formula instead of just a length top minus bottom or right minus left. But as you can see in this next section, that our volume is going to typically, let me start this. So this is this big chunk here. So our formulas are still going to use that same top minus bottom and right minus left. So one thing to notice is that the bounds, whether we're horizontally or vertically simple, they're going to stay the same when we do volume by cross sections as when we did area. So for vertically simple, our top bound is right and our bottom bound is left. And for horizontally simple, our top bound is the top, our bottom bound is the bottom. And you can see that here, we're essentially just applying different area formulas to our function top minus bottom and right minus left. So depending on your instructor, they may have you memorize these formulas or just be aware of them. But I've gone ahead and listed them all here in case it's something that you need a list of. And these formulas come from the different formulas for the shapes. So for example, you can see that for square, we just take that function and then square it. For semicircle, we're essentially pi r squaring it, but we have to have this dividing by 8 to adjust, and the same for circle, and the same for equilateral triangle. So these are really just a quick reference for you to have them all in one place to memorize, because it works the exact same setup. We just have to put it into these different formulas. So volume by cross sections is really similar to area. And the one that's going to be different is going to be volume rotated around an axis. So that's this next section here. So whenever we're finding the volume of a region rotated around an axis, there are going to be 3 different shapes that this can make. So these are going to be discs, washers, and shells. So just to kind of sketch them for you, a disc is just going to be basically a circle, right, that's going to be filled in. Let me draw that a little bit better for us. So a disc is just going to be a circle, and we find the areas of these circles and add them up. But depending on the shapes we're looking at, these discs aren't always going to have the same area. These areas could get smaller, and we're just adding them up to kind of make the shape that we end up with. The next one is washer, and so that's really similar to the disc, and your instructor may call these the same thing. And that's just basically a disc with a hole cut out of it. So you can imagine, if you've ever played the game washers, that's like horseshoes, that this is where it comes from. Or if you build things often, then you are familiar with washers. And again, these washers have different sizes, and so we're adding them all up into whatever shape our region is making. You can see these both kind of made cones, and then we're just adding them up. And the last one is going to be shells. And the shells, to me, look like a Coke can or a coffee mug, where it's going to be cylindrical, but it's going to be hollow inside. And so this is why people talk about it like a Coke can. So it's really just barely kind of this thickness of like a Coke can or a coffee mug that's empty. Right, so that's going to be a shell. And so for discs and washers, we have formulas to memorize that deal with the area of that disc and washer. And because the shell is hollow, the formula to memorize there has to do with the surface area of a cylinder. And so if the question tells you to use a certain method, discs, washer, or cells, you need to be able to set up the question or set up the integral and kind of visualize the graphs to use one of these methods. But if the question leaves the method up to you, then depending on the axis that we're revolving around, we are going to use different methods. So if we are a vertically simple region and we have a vertical axis of revolution, then that's going to use this shell method. If we are vertically simple, but we now have a horizontal axis of revolution, this is going to be either disc or washer, depending on if our region is touching that axis or if there's going to be a hole. So for example, with this middle picture, if our axis was here in the middle, then we have this hole because our region, I'm going to color here in blue. So the region that we are finding the area of was not touching that axis. The axis was in the middle of that hole, versus in our disc example, if our region was up here, right, the region we were taking was directly touching that axis. So it depends on if our region is touching our axis or not, but if the axis of revolution is perpendicular to the simplicity, we're going to use discs and washers. So therefore, if we're horizontally simple with a vertical axis, we're going to use discs or washers. And if we are horizontally simple with a horizontal axis of revolution, we're going to use shells. So again, like the other kind of resources so far in this course, that this is going to be a lot of just kind of compiling all of the things for us to memorize, right? So I'm going to go ahead and erase this highlighting. And then we have some more formulas that, again, depending on your instructor, you may or may not be asked to memorize or be aware of. But again, just to kind of highlight the similarities between vertically simple is that for all of these, our bounds are going to be the same. The top bound is the right, the bottom bound is the left. Our integrand is what's changing. So for discs, like I said, it's just going to be pi r squared, where our r is our function. For washers, it's going to be a difference of areas of a circle, pi big R squared minus pi little r squared, where we can identify a larger and smaller radius. And then for shells, that formula is the surface area of a cylinder. So 2 pi times our radius times our height. And so that's where our height is going to be the x, and our radius is going to be top minus bottom here. So this again is a catch-all, a formula list for you to have, where a lot of the work is going to come in with making that integrand. So our intersection points are always going to become our bounds. And then our integrand is where a lot of the work is going to happen. So specifically, if you're struggling with volume by revolution and that setup, the same place where you found this worksheet, there is a link to a Desmos activity on the different methods for volume by revolution. But that is going to be all for this video. We hope this helps, and good luck.